Hello everyone. So in this video we are starting a new chapter. Okay. So we are going to talk about number, but we are going to mostly focus on integer number. And then we are going to see some properties, some operations that we can do on integer number and properties of each operation. So let's see first about real number. Real number means actually all the real numbers. Okay, so real numbers can be both integer number and the number that has the decimal point. All right, now if we think about real number, real numbers has actually certain properties. Each of the real number has certain properties. Let's see if a, b and c, they are real numbers. They follows the following properties. So for example, the first one is closure, means a plus b and ab. So here ab means actually it's the multiplication. Okay, so instead of a multiplication b, in many cases actually we are going to use ab, which will represent the multiplication of a and b, two numbers. So closure property says that a plus b, if a, b and c are real numbers, then a plus b and a multiplication b both will be real number. So the property 2 says that a plus b will be uh, same as b plus a, and a times b will be same as b multiplication a. So associativity says that a plus b plus c, it's same as a plus b plus c. Okay, and identities with summation is a plus 0 will be same as a times 1, means a multiplication 1 will be same as a. All right, and it follows distribution. Like if it likes that, then we can actually distribute the multiplication both b and c. So a multiplies b plus a multiplies c, or here also we can distribute the multiplication over a and b. So additive inverse a plus minus a means this is going to cut each other out and it will become 0. And multiplicative inverse a times 1 by a will be 1. Okay, if a is not 0. All right. Uh, all right. And if we add c on both sides, all right, then it will become, if we add the same number on both sides, then it will become same. All right, and for example, like here also. Okay, so these are the couple of properties that the real numbers meet those of the certain properties. Now in this chapter we are going to mostly talk about integer number. So integer number is a set of number that doesn't has the decimal point. Okay, so integer number means they are just a subset of, and they are proper subset of real number. Okay, we know the difference between subset and proper subset, right? So integer number are the proper subset of real number. All right, so now not all the properties of real number are the properties of integer number. Okay, integer number are just the proper subset of the real number. And one fact of real number is that there are subset of real number, even the positive real number, that doesn't have any smallest element. So this fact has a special name. It is known as well ordering principle. So a well ordering principle says that a non-empty set of natural number has a smallest element. What does that mean? Let's see, we have a n stands for set of natural number. Okay, say 1 2 3 like that. But if we think about any non-empty set of natural number, it may start with 1, but it may start with any other number. All right, any set of natural number, non-empty set of natural number, that will have a element that has the smallest value. Okay, for example, just think about a one set like that, say 4 5 6 8 3 7. Okay, So any non-empty set of natural number, we are talking about natural number. Natural number means actually all positive integer and doesn't all positive integer. Okay, so in that case, all set of natural number, in that case we can say that if we have a set of natural number, in that case there will be a smallest element. Okay, so in any number there will be one element which will have the least value, okay, smallest value. So in this set we have the smallest value. The smallest value is 3. Okay, if we just sort all the numbers based on their value in ascending order, the first element will have the smallest value. Okay, now a non-empty set of natural number, a non-empty set of integer value actually has a OL ordering principle. Okay, so a non-empty set of integer value, okay, set of integer values, or if we think about just the set of integer value, okay, they follows the OL ordering principle. So OL ordering principle says that if we have a non-empty set, then in the set there will be a smallest element. Okay, there will be a element that has the smallest value, okay, a least element. Now what about the real number? So the fact about real number is that there are subsets of real number. Let's see, if the real numbers are positive, they do not have any smallest element. What does that mean? So let's see, we have a set where we have some couple of real numbers. Okay, they all are part of real numbers, and the real numbers look like this. Say uh, 1 1 by 2, okay, then 2 to the power 2, 1 by 2 to the power 3, 1 over 2 to the power 4, like that. Okay, and all the numbers are decreasing and decreasing and decreasing, and it is going to be infinite. It is going to continue, and you can see that as we are continue with this pattern, the numbers are getting smaller and smaller, and we cannot actually say that which number is going to be, which number has going to have the smallest element, because this is the part of real number, so any smallest element here is possible. All right, but this is different in the integer number. A set of integer number, a set of integer number is going to have a set of integer number is going to have a smallest element. Okay, so a set of what actually we are trying to say, a set of non-empty natural number is going to have a smallest element. So if a set can have a smallest element, in that case we can use a proofing technique known as mathematical induction. Okay, without having a smallest element in a set, we cannot use the idea of mathematical induction to prove some mathematical statement. All right, so we are going to talk about more about this OL ordering principle in our next chapter, chapter 5, when we are going to learn details about mathematical induction. Okay, but for now just remember, a OL ordering principle means a non-empty set of natural number will have a smallest element. All right, so let's talk about an operation that we can do in integer number. Okay, so here this chapter is mostly about integer number, so all the operation we're going to talk about, we're going to focus on integer number. So division. So we are familiar with division. If we have two numbers, we can actually divide one number by another number. All right, now let's see all the mathematical aspects of the division algorithm. So what does a division algorithm, how does a division algorithm works, and um, how can we define this algorithm, how can we define this operation? So let's see, we have two numbers a b that belongs to integer number. Okay, I'm reminding you again, this chapter is mostly about integer number. So given two number a b belongs to z, okay, b is not 0. Okay, uh, So here it should be a is not 0. Okay, so a is a divisor of b, and we say that b is divisible by a. And the formula we write it like that, a division is like that, a divides b. Okay, which means that b is divisible by a, or a is a divisor of b. Okay, so or we say that a divides b. So this is read as like a divides b. A is a divisor of b, or a factor of b, or b is divisible by a. Okay, so we say that a divides b if and only if there is an integer number q, all right, such that we can represent it like that, a times q equals to b. All right, so where q is a integer number. So let's see an example. Let's see, we're saying that 3 divides 15. How, when we can say that 3 divides 15? So if we can represent 15 like as a 3 times some number equals to 15. Okay, 3 times some number equals to 15, where that number, which is q, belongs to an integer number. Okay, and we know we can represent it like as a 3 times 5. So 3 times 5, 5 is an integer number, and we can represent 15 as a 3 times 5. Okay, or let's see an example, another example. Let's see 4 divides 16. Okay, we'll say that 4 divides 16 if we can represent like that, 4 times some number equals to 16, where this number belongs to a integer number. So looks like 4 times 4 equals to 16, and 4 belongs to integer number, so we can say that 4 divides 16. Okay, so here 4 is the divisor of 16, and we say that 16 is divisible by 4. All right, now so that's how division looks like. Okay, that's how division looks like, and here we are saying that it is going to be actually a not equals to 0. So we are saying that we do not know, we cannot divide any number with 0. All right, so it will become infinite, but we cannot divide any number with 0. So any number which is not 0, okay, for that we can say that a divides b. It signifies that b is divisible by a, or a divides b. Okay, and where I can represent b as a times q, where q belongs to some integer number. Now for this division, operation follows some property. Okay, we are going to look at some properties, and we are going to see how we can prove them. Say for example, if a divides b and a divides c, we can say that a will divide b plus c. All right, so let's try to prove that. So we are saying that a divides b. So that means actually we can represent the whole thing like that, a times c1 equals to b, where c1 belongs to some integer number. Okay, and again we are saying that a divides c. So all right, so let's use just a different number, k1. Okay, so where k1 belongs to integer number. So we are saying that a divides c, so we can represent that as like a ak2 equals to c. All right, where k2 belongs to one integer number. All right, now let's find out b plus c. Okay, and to prove that we have to prove that we have to be able to represent it like that, a k3 equals to b plus c. Okay, where k3 will belong to some integer number. So if we can find out this formula, okay, this property is a valid property. Okay, that's a valid statement from given this. We can say that a is going to divide b plus c, right? So let's find out b plus c. So here b plus c is a times k1 plus a times k2. Okay, simple. So A times k1 plus k2. Alright. Now k1 is an integer number and k2 is an integer number. Okay. So if we have two integer number, alright, if we have two integer number and if we add them, the result will be also an integer number. Say for example, if we have integer number 2 and if we have another integer number 3, so it follows the closure property. Okay, it is known as the closure property, that if we add two integer number, that will return another integer number. So k1 plus k2, if we say that k1 plus k2 is k3, okay, then k3 is also another integer number. Okay, and here you can see that we can represent the whole thing as like that: a k3 equals to b plus c, and where k3 belongs to a integer number, so that proves that a divides b plus c. All right, so the next property says that if a divides b, then a will divide bc, okay, for all c belongs to integer number. So this is like that. Say if a let's see, if 2 divides 4, okay, then 2 will divide all the b times c, where c belongs to a integer number. Okay, now let's say this one is our b, so 2 is going to divide like 4 times 2, 2 is going to divide 4 times 3, 2 is going to divide 4 times 4, like that. Okay, and c can be here 2, 3, 4, any integer number. So let's try to prove that with our division properties. Okay, so we are saying that a divides b, so that means a k1 equals to b, okay, where k1 belongs to an integer number. All right, now to prove that I have to find out whether I can represent the whole thing like as a k2 equals to bc, where k2 belongs to integer number. All right, so here also we can do the same. Let's multiply both of the side with a integer number c. Okay, a times k1 times c equals to b times c. Okay, now what about this number? All right, so the closure property says that if we have two integer number, their multiplication will be also an integer number. So think about like that: if we have any two integer number, their multiplication is going to return another integer number. Okay, so 2 times 3 or 4 times 3, you can actually try to disprove that, but that's the closure property of integer numbers. If we have two integer number, their multiplication will be a integer number. So we can assume that now k2 equals to k1 times c. All right, so a k2 equals to bc. So if k2 equals to, as k2 equals to an integer number, we can say that a is going to divide bc. Okay, a divides bc. All right, so the third properties. So our third property is if a divides b, then if a divides b, if a divides b and b divides c, we can say that a will divide c. Say for example, one example, if a 2 divides 4 and 4 divides like 16, we can say that here 2 divides 16. Okay, now let's try to prove that. So a divides b means we can represent it like that: a k1 equals to b, where k1 belongs to an integer number. Okay, and we have b divides c, so from b divides c we can say that b k2 equals to c, where k2 belongs to integer number. All right, now to prove that given these two statement, I have to prove something like that I can represent a k3 equals to c, where k3 is also and k3 belongs to an integer number. So if I can prove that, I can say that a divides c. Okay, all right. So let's use this one, because here I have bk2 equals to c and I know the value of b from here. Okay, so let's replace b using a k1. Okay, b equals to a k1, so I can use this fact here, a k1 times k2 equals to c. And now what about k1 and k2? So k1 is an integer number, k2 is an integer number, and we know the closure property. So the multiplication of two integer number is going to be another integer number. Okay, so let's see k3 be k1 times k2, and we know from the closure property, this is known as closure property, is multiplication of two integer number is also an integer number. Okay, so we can write it like that. All right, so we can say that a divides c. Okay, all right. So in all of those algorithm, we saw that when a divides b. Okay, now if a divides b, that means actually we can represent a divides b is like a times c equals to b, where c is an integer number. Okay, all right. Now let's see think about some two numbers where a one number may not evenly divide the second number, means like a may not evenly divide the a may not evenly divide b. Okay, for example, if I think about 4 and 21, what about that? So if I if I am trying to represent it like that, 4 times some number equals to 21, so this number is not going to be a integer number. Okay, it is going to be some real number, some decimal point, because 4 doesn't evenly divide 21. Okay, and we can think about like high school mathematics, how we can find it, like 4 times 5 equals to 21. So here I can represent it like that. So 5 is the 5 is the number known as quotient, and there is going to be a remainder 1. Okay, all right. So for this such of case, we are going to have come up with a new value known as remainder. Okay, not every integer value is going to divide every other integer number. Okay, so if a number doesn't evenly divide another number, in that case in the division algorithm, I have to come up with another number known as remainder. Okay, so for example, here 5 is the quotient, it is known as actually quotient, and 1 is the remainder. So in that case, given a b belongs to natural number, okay, where b greater than 0, there exists a unique pair of q and r. Okay, and q and r is going to be, it can belongs to n union n means all the natural numbers, and we are going to do the union with 0. That means is the all number starting from 0 and all the natural number. Okay, such that we can represent each number as a q times b plus r. Okay, and where r will be between 0 and b. Okay, all right. So for example, like here in this example, like any number, I can represent it like that. So if I have a number 21, Okay, if I have a number 21, and in this example actually I'm thinking about a equals to 21. Okay, and I want to divide a by a divisor 4. Okay, so how I can represent a with using this formula qb plus r. So I can represent a 21 like this. Okay, 4 b equals to 4, 4 times some number plus some number r. Okay, so this one will be my q, this one will be my r. Okay, and the value of r can be, it can be 0. Okay, but it is going to be between 0 and some other between 0 and the divisor. Okay, so here just be sure that here we are just reversing the role. Okay, so here a is the number, and a is the number, b is the divisor. Okay, b is the divisor. We are trying to divide a by b. Okay, now I can represent it like that: 4 times 5 plus 1. Okay, you can see that 4 times 5, 20 plus 1 is 21. So I can represent a equals to 4, which is my divisor. Okay, b plus b times some number q and some number plus some number r, where both q and r is going to belong in union 0. All right, so you can see that they are actually all the natural number, means all the positive integer including 0. All right. Alright, now let's see another example how I can represent 21. So what if I am trying to represent 21 as like that, say 4 times 4 plus 5. Still it's a valid statement. You can see that 4 times 4 is 16 plus 5 is going to give me 21, and it's the same formula, but it's not actually the correct representation, because we are saying that the value r has to be less than the divisor. Okay, value r has to be less than 4. Okay, and okay, it can be 0, but value r has to be less than 4 here, the divisor. But here we can see that 5 is greater than 4, so that's not the way we can represent a division algorithm. Here what we have to do actually, here we have to increase that by 1. Okay, and decrease it by 4. All right, now I can represent like 16 as if our a equals to 16 and b equals to 8. Okay, I can represent it like that: 8 times some number plus some number. Now in that case it will be 8 times 2 plus 0. Okay, so we say that here this value is q, this value is r. So and their name are like q is known as quotient and r is known as remainder. Okay, so and remainder has to be in between 0 and b. Okay, it has to be a value greater than or equal to 0, and it has to be less than b. All right, so and here we are dividing a by b. All right, b is the divisor, so that gives us a way to encode a by b using only positive integers. Okay, so we are dividing a by b. All right, we are dividing a by b, but we are using only the positive integers. So in that case we need two numbers, one is quotient and another is remainder. So let's see some other examples. Let's find out the quotient and remainder for each of these division. So as we say, we are going to represent a equals to like that: b times q plus r. And remember, r has to be greater than or equal to 0, less than b. All right. All right. So in this example, here we have a equals to 18, b equals to 7, okay. So we are going to find out what will be our quotient and remainder. That means we are going to represent 18 equals to 7 times some value plus some value, okay. So that will be our q and that will be our r. So we can find out that 7 times 2, we can actually find out that like that, say 7 times 1, and that will give us 11, right? But 11 is greater than 7, so that is not going to work. So 7 times 2 plus 4, okay. So that is going to work because 4 is less than 7, okay. Here 11 is greater than 7 and here 4 is less than 7 and this is greater than 0, so it works. Now if we think about like that, 4 times 3, which is 21, so I have to make it minus 21 minus 3, okay. But here my remainder r, okay, r is less than 0, so none of the condition works, so only this condition works, okay. So here the quotient would be 2 and r would be 4, okay. So q equals to 2 and r equals to 4. So let's find out this one. So here a equals to minus 112 and b equals to 10. So I have to represent it like that, 10 times some number plus some number. Alright, that would be my q, that would be my r, okay. So you can go over like all of this and find out for which our the condition for r is correct, okay. Alright, but let's see what it will look like. So here it's a special case where a is less than 0, okay. So let's find out. So let's see, we choose q equals to minus 11, okay. So what happens? So if q equals to minus 11, then we find out minus 100 means our r has to be minus 2, okay. So that will give me minus 112. But as we know that r has to be between 0 and b, okay, r cannot be less than 0. So what I have to do here, I have to actually add 1 here, like minus 2, minus 12. All right, so that means it will be minus 120 plus 8, that will give me minus 112. So that is my correct answer. All right, that is my correct answer, because now I cannot I cannot make it minus 13. In that case r will be greater than b, okay. So here my value of q equals to minus 12 and r equals to 8, okay. So remember, r has to be a positive number between 0 and less than b, okay, less than 10. All right, now let's find out this. So here that's also a special case where our a equals to 0, okay. Our divisor cannot be 0 in the division algorithm, but a can be 0. So here a equals to 0, b equals to 14. So we have to find out, we have to represent a equals to like b times some number plus some number, okay. All right, so here it's actually simple, we have to make it all 0. So b times 0, it's 0 plus 0. So here quotient is 0 and remainder is also 0, okay.